Let's pick up where we were at the very end of this problem here. We were talking about this very last part. When is the velocity positive? And that's the only thing we hadn't answered yet. The velocity is going to be positive when the function's greater than 0. So we're going to do the same thing we did, except we're not going to set it equal to 0. We're going to say greater than 0. And again, we're looking for a t-value, and we can see here that's the only variable that we have. So from the work that we did over here, when it equals 0, we know that the velocity is going to be positive for any t-values beyond 3 seconds. All right, so the second derivative of the position function would give us acceleration. So velocity is different from speed. I want you to recognize that. Velocity, and you'll get this, more than you could ever hope for probably in physics. Velocity is movement with direction. Okay, that's different from speed, which is just movement, ignoring direction. There is a definite difference between them as far as, real world meaning. Velocity can be positive or negative. You can be moving in the positive direction. You could be moving in the negative direction. Speed, mathematically, we say that speed is the absolute value of velocity. So when we have speed questions, all we have to do is find velocity and take the absolute value. In other words, make it a positive value, because we're ignoring direction when we talk about speed. So I want to make sure that mathematically you understand what that means. Here is Leibniz notation for the second derivative. The first derivative in Leibniz notation was the derivative of y with respect to x. The second derivative is denoted as d2y dx2. Now, it's a little more clunky than a second derivative in function notation. In function notation or prime notation, one little apostrophe there was the first derivative. In function notation, two little apostrophes are going to denote the second derivative. And again, you need to know both of these notations, function and Leibniz, because you're going to see them both. Equivalently, this could be y double prime. You're going to see them both on the AP exam and therefore on my quizzes and exams. Leibniz, it may look a little clunky, but it just means the second derivative. So make sure that you know that notation. So if velocity measures the rate at which position is changing, then acceleration, which we call A, measures the rate of change of velocity. So acceleration is the derivative of velocity. And therefore, the second derivative of position. So acceleration tells us the rate at which the rate of change of position is happening. So let's look at this notation-wise. If we have a position function, and I will tell you lots of times you're going to have a position function given to you as x of t, not necessarily s of t. So let's say that they gave us x of t, which is some manipulation on t, and we're calling that function x. Velocity is going to be x prime of t, or equivalently dx dt, and acceleration will be x double prime of t, or we could say d2x dt2 We could equivalently say it is v prime of t, or the derivative of v with respect to t. Acceleration has many, 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 many symbols, and we usually see that as a of t. We're usually going to see this as v of t. So position, velocity, acceleration. So make sure you could go through all those iterations of notation for acceleration. All right, acceleration is the derivative of velocity with respect to time, which is the derivative of a function, usually position, with respect to time. All right, so same question, same position function, the same setup on the question anyway. And it wants to know what is the acceleration of the object. Well, remember the velocity of the object was 4t minus 12. So the acceleration of the object is the derivative of velocity, and we can see that that's 4, and it's going to be centimeters per second, which we can write as centimeters squared. So the velocity is increasing at a constant rate. It doesn't depend on any time t. There's no t in acceleration. We have a constant acceleration. It's helpful to think of time in 3 general categories, although frankly, there's just 2 categories that we see most often. But I do have students occasionally ask me about this. Why is it every time we have an object motion or a particle motion, they generally give us that definition for the domain of the function when we're talking about position, velocity, acceleration? So they say, well, can we not have any negative time values? Well, in some context, negative time is meaningless. In other words, they want to know, why do they even tell us this? Don't we automatically know that? Well, let's look at something really quickly. Let's say that we're given a list of values of, something that's happening at 1960, something that's happening at 1980, something that happened in 2000, and, we're given some sort of position function that says, here's what's going on with those. And let's say we call this t equals 0. So we would call this t equals 20, and we would call this t equals, I guess I shouldn't say equals, we could call this t equals 40. So if we're going to say that at time t equals 0, we're beginning in 1960, could we take this and could we determine what was happening and if it has any meaning, let's say, to what was happening in 1940? Well, yeah, we could. In that context, past time, if we're calling, this t equals 0, then some time in the past could be considered time prior to t equals 0. I've actually never seen that as a question on the exam